Good afternoon, everyone. I'm going to talk to you today about magnets. So the first thing I want to mention is the Tesla. So the Tesla is a unit of measurement basically describing how strong a magnetic field is. So on one end of the spectrum, we have the Earth's magnetic field, which is pretty small, 0.0005 Teslas. And on the other end of the spectrum, we have our world record-breaking magnets at the Mag Lab, and the magnets that we use to control little hurricanes, but I'm just kidding. So, and in the middle, there are magnets that we use to hang things on our fridge, and these are permanent magnets. Now, permanent magnets don't need any electricity to stay a magnet, but then we also have electromagnets, like the magnets we see in MRIs. And essentially how these work is you have electricity flowing through a wire, and that is what creates your magnetic field. Then we have superconducting magnets, which are a special type of electromagnet where when cooled down, very, very, very cold, they lose resistivity, so you can produce very, very high magnetic fields. And these are the type of magnets that you would see that I work at the Mag Lab, and that we need to build things like fusion reactors, since you need such high magnetic fields. So the project that I work on is the 40T project. So we're trying to build a 40 Tesla magnet that can run for extended periods of time and can be used for physics experiments. And you can see here that there are these like coils made out of tapes. So the magnet is going to be made of tapes that are wound around each other to make a coil. And when you have these tapes, this coil is composed of these tapes and high magnetic fields, you have really high forces, and then you get deformation or strain. And that can be a problem when you're designing magnets, because as you can see in the picture, that can cause the tapes to tilt, that can change what's going on with the magnetic field. And also, if the deformation is too much, you don't want the properties to change and the magnet to melt or explode or anything. So to prevent that from happening, we use numerical analysis when we're designing our magnets. Now, numerical analysis is really important because building these magnets is really expensive and experiments are expensive. So before we do these experiments, we need to design using simulations. And as an example, this is a simulation of a test coil that I did, and you can see the magnetic field over time. And in the center is where you get really high, or the most high magnetic field. And then from that, I can model one disk out of the test coil and then look at the strain over time that's going on in the disk on the tapes. So why is this important? Why do we care? Besides the fact that superconducting magnets are really cool and fun. So medical applications, like I mentioned before in the other slide with the picture of the MRI, higher superconducted magnets can be used for imaging. So the higher field, the more that we can look into our bodies and then diagnose diseases, cancer. And like in the previous presentation that was mentioned with the super collider, there's an image up there, and we need superconducting magnets to actually build those super colliders. So they're used for physics research. And then also clean energy. In order to build a fusion reactor, we need high field superconducting magnets. And in addition, superconducting magnets can be used to make very, very efficient motors, which hopefully someday can be used to make electric airplanes and other electric vehicles, cars. So thank you, everybody. I hope you learned something.